Our third topic in this unit was the colligative properties of solutions. Colligative properties are properties that occur whenever a solute is dissolved in a solvent, and it doesn't matter at all what that solute is. All that matters is how much of that solute is dissolved. So it wouldn't matter if you're dissolving salt in water or sugar in water. You'll see all these colligative properties. And the only thing that would affect how extreme these colligative properties are is how much of those solutes you add. There are four we're going to look at: freezing point depression, boiling point elevation, the increase in osmotic pressure, and decrease in vapor pressure. Of those four, we're going to learn a little math with two of them. We're going to learn how to calculate the freezing point depression and the boiling point elevation. We'll start with freezing point depression. Whenever a solute, any solute, is added to a solvent, its freezing point will drop. In other words, you'll have to get it colder to freeze it. As you should know, water freezes at 32 degrees Fahrenheit, 0 degrees Celsius. If you add salt to water, you can push that freezing point down. The more salt you add, the lower it goes. So you can push that freezing point of the water all the way down into the teens, 13, 14, 15 degrees Fahrenheit, 7, 8 degrees below 0 in Celsius. This is why we put salt on the roads when it snows. When that snow melts and makes liquid water, we mix salt into it so that that water won't refreeze in the cold. It pushes that freezing point down into the 20s, maybe into the upper teens, depending on how much salt you dump on the road and how much of it actually dissolves. But in doing that, you keep that water from refreezing on the roads at night. At the same time, the freezing point drops, the boiling point goes up. So basically what you're doing is you're spreading out the temperature range at which the substance, the solvent, stays liquid. You're pushing that freezing point down, you're pushing that boiling point up. And again, it doesn't matter what solute you use, any solute will do it. The more you add, the more it goes up. Now, I will say the boiling point elevation is less than the freezing point depression. In other words, the freezing point will drop more than what the boiling point will go up. For my example here, we're talking about making candy, and making candy, you mix sugar and water together, and you boil that mixture. And you can get that boiling sugar water up to 300 degrees Fahrenheit at an 80% sugar concentration, well above the boiling point of water, which is 212 degrees Fahrenheit. And again, the reason why this boiling point goes up is because the sugar is there. That solute is pushing that boiling point up. The third colligative property is a change in osmotic pressure, an increase in osmotic pressure. You learned back in biology that whenever you have two solutions of different concentrations separated by a semi-permeable membrane, the water will move from the area of high concentration of water to the area of low concentration of water. And this is tricky because when you see the strengths of the solution are often measured in and related to the amount of solute you have. This will probably look kind of familiar to you from biology last year. So we have a solution. Outside, I've got 5% NaCl. And inside, let's say, I have 10% NaCl. Back in your biology class, it has a horrible 10%. Inside you have 10%. Should have made my little thing bigger. You know what it is. You have 10% NaCl inside. You learn that this is a hypotonic solution. In a hypotonic solution, water is going to flood into this cell or across the semi-permeable membrane to try to balance it out. What we have to do when we think about osmosis is flip those numbers. That is not a 5% NaCl solution. That's a 95% water solution on the outside. That is not a 10% NaCl solution on the inside. That is a 90% water solution on the inside. The water is moving from where you have more water to less water. And the process by which it moves is called osmosis. Now that's important to know because this is osmotic pressure. It's obviously related to that. Osmotic pressure is the amount of pressure it takes to stop the osmosis from occurring. The amount of pressure it would take to stop the water from moving across that semi-permeable membrane. And the way it works with colligative properties is that the greater the amount of solute you add, the more solute you have, the greater the osmotic pressure. The more solute you dissolve, the more pressure it takes to stop osmosis from happening. And the best way to think about this is in terms of a concentration gradient. So again, let's say I've got pure water, 100% water on the outside. And on the inside, I've got 5% solute, at 5% sodium chloride. That means on the inside, it would be 95% water. That's a pretty small gradient. That's a pretty small difference from one side to the other on my semi-permeable membrane. So this water is going to be trying to move this way, but because the difference is so small, that flow of water is pretty weak, and it's pretty easy to stop it. But let's say I had 100% water on the outside, and on the inside, I've got a much larger amount of solute. Let's say it is a 40% salt solution. That means I've only got 60% water on the inside this time. That creates a much higher gradient, a much steeper gradient, which means the water is going to be trying a lot harder to get to the other side. It's going to flow much faster, it's going to flow much harder, which means it's going to be much harder to stop it. So that increase in the amount of solute is going to increase the amount of osmotic pressure needed to stop osmosis from occurring. The final of our colligative properties is vapor pressure. And vapor pressure is important because vapor pressure is related to the boiling point of the substance. And in fact, it is the vapor pressure change that is responsible for the boiling point elevation. Vapor pressure is the pressure of the solvent particles in the gaseous state above the surface of the solvent. It's produced by evaporation. Make you a little drawing here. We have a solvent here, like water. And I hope you can see that. Hopefully your screens aren't too small that you can't see all these little red dots I'm drawing. These represent my water molecules. And because of evaporation, some of these water molecules are going to leave the liquid and go into the gas. So you're also going to find some water molecules up here above the surface. Those water molecules that are above the surface are going to push back down on the surface of the water. So they're going to apply a pressure on the surface. They're going to bounce off of it. They're going to push down on it. That pressure they apply is vapor pressure. And every one of them are going to push back down on it. So the more particles we have up here, the greater that vapor pressure is going to be. When we add, I can't really draw it on now, but you notice it. The more solute we add to this solution, the fewer solvent molecules you're going to see in the air above it. So when I add a solute, not only will I be adding particles down here in the solution itself, some of these solute particles will end up on the surface. And what those particles on the surface do is they block some of these solvent particles and keep them from getting out in the first place. So if I have a solvent particle here, it's blocking some of this stuff from getting out. And so what you'll find is when you add solute, there'll be less evaporation, there'll be fewer particles in the gas above the liquid, and as a result, you'll see your vapor pressure decrease. Now, this is important because vapor pressure is the factor that determines where a substance will boil, or what temperature a substance will boil. A substance boils when its vapor pressure is equal to atmospheric pressure. So if I've gone and cut the vapor pressure down on my solvent, I'm giving it a further way to go, a greater distance it has to go in order to get up to the atmospheric pressure, which means you're going to have more heat. It's going to take more energy to get more particles to leave the liquid and go into the gaseous state. Math-wise, we learned how to calculate freezing point depression and boiling point elevation. They're pretty simple. They're just equations. It is equal to I, which is the Van Hoff factor, times K, which is either the freezing point depression constant or the boiling point elevation constant, depending on which one you want to do, times M, the molality from the previous video of your mixture. Now, I, the Van Hoff factor, is easy to figure out. If it's a covalent substance, something that has no metal in it, the Van Hoff factor is just 1. If it's an ionic compound, it's about the number of particles you're going to get for every formula unit. So what that means is really, really simply, you have to see how many particles, how many ions are in that formula. And this formula has 1 calcium ion and 2 chlorine ions in it. And 1 plus 2 is 3. There are 3 ions you'll get for every formula unit. And it really is just as simple as counting the number of atoms in most formulas. The only time that you wouldn't be able to do that is when you had a polyatomic ion. So let's say you had MgNO3, magnesium nitrate. The reason this one's a little trickier is because the Van Hoff constant or Van Hoff factor isn't the number of atoms in the formula. It's literally the number of ions, what it really is. And what you would have here is 1 magnesium ion and 2 nitrate ions. See, the nitrate is covalently bonded. So the nitrate's not going to split into nitrogens and oxygens. It's going to stay together as an NO3. And as this little number right here tells me outside the parentheses, there are 2 of those nitrates. So my Van Hoff factor for this one will be 3. If there are no parentheses around your polyatomic ion, that means you have just 1 of them. I think that's the trickiest part of it. K is a constant. It's different for every substance. For water, it is 1.86. And I'm going to write that down real quick so I don't forget it. 1.86. Because when we do the math, as we're going to do over here, we need to remember that. So we're calculating the freezing point depression when 85 grams of K2S is dissolved in 500 grams of water. First thing we got to do is figure out our molality, lowercase m. That is moles of solute over kilograms of solvent. So first thing we're going to do is figure out how many moles of K2S we have. For that, we need to know the formula mass, because we're going to do a little mole mass conversion. So potassium is 39.1. We have 2 of those plus 32.07 for sulfur. So 110.27. So to find my moles, it's 85 grams times 1 mole over the formula mass. So 1 mole over 110.27. I'm just going to use 110. So 85 divided by 110 is 0.77. So let's just go ahead and call it 0.8. That's the number that goes on top. My number on the bottom has to be kilograms of solvent, but I'm given grams of solvent, which means I have to do a metric conversion. King Henry died by drinking chocolate milk. I am going from my base unit to kilo, which is 3 places to the left. So 500 becomes 0.5. So it's 0.8 divided by 0.5. Which is 1.6. That's my molality. My freezing point depression, delta TF, is equal to my Van Hoff factor. This is an ionic compound, so I just got to figure out how many ions I'm going to get. I'm going to get 2 potassium ions, and I'm going to get 1 sulfur ion. So it's a total of 3 ions times K. And for freezing point depression, K is 1.86. Wow, that's about 8. Again, having to write with my mouse because I can't use the touch screen with this, so it's Screwcastify. Times my molarity. So 0.3 times 1.86 times 1.6. So 0. I put 0.3 in. 3 times 1.86 times 1.6. 8.92. So my freezing point would drop 8.9 degrees Celsius. If we're talking about pure water, that means it would freeze at negative 8.9 degrees Celsius. If you wanted to figure out Fahrenheit, you'd have to convert it to Fahrenheit. Boiling point elevation, and I throw it in here too because it's the same equation. We just have to change these. Let me click. There we go. We just have to change these F's to B's. What I forgot to do. But the equation is the same. You'll get to see it corrected.
Please pardon the interruption. Track practice for today is canceled due to weather. Again, track practice is canceled due to weather.
So it's the same thing. I is still the Van Hoff factor, and it's still just the number of ions you're going to get, one for a covalent substance. Kb is a constant again. This time it's 0.52 for water. So our freezing one and our boiling one are 2 different numbers. The freezing one is smaller or is larger than the boiling one. That's why the freezing point depression is greater than the boiling point elevation. And M is still molality. So again, same math. I actually have the same numbers here. So we have 85 grams of K2S. We already converted that to moles right here. That was 0.8. We have 500 grams of water, which we already converted into kilograms. That's 0.5. So our molality was 1.6. Again, we already did this, so I'm not going to do it a second time. Videos are already probably long enough. If you have grams of solute converted to moles, that's the number on top. If you have grams of water, it does have to be kilograms, so you do a metric conversion on that. Your delta TB equals your Van Hoff constant, which a factor again, so that's 3 because we get 3 ions there, 2 potassiums and 1 sulfur, times K, and this time it's boiling, so it's 0.52. If it weren't water, it would be a different number. Every substance is different. Times 1.6. And if it was a different substance, I would tell you what K is. So 3 times 0.52 times 1.6. So 2.5. And again, my boiling point elevation is less than my freezing point depression. It would go up 2.5 degrees Celsius and it would go down 8.9 degrees Celsius at the same time. All right, there's one more section to go. That's acids and bases. I'll make that video once I've covered it. I'm almost out of time anyways today. So we'll see you then.